So what do I mean by that? I mean, if I give you a problem like this, given a normal distribution with let's make this orange. Given a normal distribution with mu equal to 48, sigma equal to 11.21, can you find the probability that something is going to be more than 50 if we randomly select that thing? All right, that scared me for a second. So we select one item. What's the probability that that's greater than 50? So this could be ages or test scores or whatever, right? That is what I call a basic z-score problem. You're given a raw score. You're asked to find a probability. So you take the raw score you're given, you make it into a z-score, and you look up the percentage. That's section 6263, right? That I'm hoping, this should be decently easy right now. And if it's not, I want you to realize it should be. All right? Don't make too much out of this. It's not that difficult math or using the z-score chart. If it is, come see me. All right? So let's take a second and go ahead and do that. If you need to borrow a calculator, I got a few up here. And real quick, before you even get into this too far, if the mean is 48 and the standard deviation is 11, is there a decent chance that something's going to be greater than 50? Isn't there a decent chance? Because there are a lot of stuff that are far away from 48 on both sides, because 48 is kind of in the middle. It's normal. So there's a really good chance. I should get a decently high percentage. Smaller than 50% because it's on the other side of the mean. But I still should get a decently high percentage for this. Alright, so let me catch up to you guys. If you draw this picture, what goes right in the middle? 48. You're looking for 50. Just put it up there somewhere. And you want greater than 50, so you shade in above that thing. You don't need that step, really. I highly recommend that step. Drawing the picture. And then what do I do before I can find that area? Yeah, find a z-score so then I can use a z-score chart. And why really am I allowed to use a z-score chart here? Yeah, it's normal, so I can use the z-score chart. Cool. So if you make that into a z-score, my score minus the mean divided by the standard deviation. And whatever the hell that is. 0.17? 0.17? 178? Oh, that's funny. I like that because I said 0.178. So 0.18 then? Cool. So z-scores, why do we always go out to two places? Because the chart goes out to two places. That kind of makes sense. So even if you forget, when you go to look at the chart, you're like, oh yeah, two places. Then you look this thing up, and I'm always going to show you the non-shortcut way. So some of you guys understand the shortcut, kick-ass. I'm basically going to always explain it the other way, just in case you don't quite get the shortcut and don't want to use it. If you look up 0.18, you're always going to get the area below whatever you look up. So what do you get when you look up 0.18? What area do you see? So you can get away without putting it up here on the overhead. Yeah, so if I look up 0.1, and again, there's my beautiful book on display. 0.1 8, I see 0.5714. So make sure you can do that. That's 0.5714. So what's the actual answer to the question then? 0.42. 1 minus that, beautiful. So it should be 0.4286. Now the shortcut here is, by people that do know the shortcut, if you look up negative 0.18, you'll get the answer directly. If you're not sure when to do that or why that works, just never do it. You don't need it. That wasn't too long. All right, how are we feeling so far? Is that decent? That goes along with, we knew it should be a decently high percentage, less than 50%, because that's above the mean. The mean would be 50%, so that should be a little bit less, and that makes sense then. Sweet. So what happens if I take a sample of 48 items? What's the probability that the sample mean will be more than 50? Now think about it. Again, step out of the statistics for a second. For one thing to be above 50, that was going to be pretty easy. And we knew going in, I should get a decently high percentage. Should be a decently high probability that's going to happen. But for 48 things to have an average more than 50, well, what's the best guess for the average of these 48 things? Maybe that's not the best number to pick, but oh well. My brain seems to be stuck on the number 48. The best guess for the average of any sample of something I take from this is going to be the actual average of everything. That's the best guess. If it's a randomly selected sample, they should be close to this. So how likely is it that the average is going to be more than 50? It should be very small now, right? And that goes exactly along with the idea that when we take a sample, everybody rushes to the mean. My picture gets smaller, the standard deviation gets smaller. That's the idea. So what's the very first thing I have to do here? What two things have happened here that tell me what to do? The funny thing is, there's only two things here. So those two things, Jeff. I took a sample and asked a question about the sample. So it tells you what? Can I use this guy? No. No, that's the guy that's good for individuals. That was why it was perfect for this question. Individual thing. Here I'm asking for a group of stuff. I need the standard deviation that works for groups of 48 specifically, right? Yeah. So what's my standard deviation going to be now? It's going to be the 11.21 divided by square root of 48. Beautiful. N, 48. And then whatever the hell that is. 1.618. That's just the very first step. You just immediately do that. You're like, damn, they gave me the standard deviation for the wrong thing in part B. Let me make the right thing, and then all your steps are the same. You do exactly this work. The only difference is I can't use that. I have to use that. Do you guys pick up on how desperate I am to make sure that this is really not that difficult? It took me forever to explain this. And I know you felt that way. You're like, God, this guy, shut up. Right? It's fine to think that, because I was talking a lot. But it took me forever to explain it. But what actually happens nuts and bolts wise to us, that's it. So now I do the same steps. I got my picture. The mean is 48. I want greater than 50. I want to make it into a z-score. The exact same stuff we just did. It's just that when I get to this step, divided by the correct standard deviation. It's like, what, 1.24? 1.24. I like it. So now, do you see how that 50 is now much further away than it used to be? 50 used to only be 0.18 steps away. Not even a quarter of a step away. It used to be really close. Now, 50 is way the hell out there, because all the values have gotten a lot closer. 50 is now relatively much further away than it used to be. That's going to go along with the idea that we just said. The probability should be a lot smaller. It should be a lot harder for a whole group of 48 things to have an average so much above what the average should be. And sure enough, when you look at 1.24, what do you get there? Look up 1.24 in your books that hopefully don't look this bad.
0.8925.
Beautiful. 0.8925. So what's my actual answer then?
0.1075.
Yeah, 1 minus that, 0.107511. So it used to be about a 43% chance for a single thing to be greater than 50, but for 48 things to be greater than 50, there's only like an 11% chance. Because most groups of size 48 should be really, really close to an average of 50. I mean, 48. They should not be further than 50. They shouldn't be out there. All right, cool. So, that's kind of a review of 6.2 through 6.5. So not surprisingly, today we're going to do 6.6 and maybe a little bit of chapter 7. All right, so everybody got this here? Okay. What section 6.6 does, we'll put this up here. You guys will remember this thing, hopefully. Did you guys hear the study they did that showed, real quick, let me go through my hopefully related story. That show that cracking your knuckles does not cause arthritis. I mean, that's an old wives' tale. They've done studies before. This was large enough and reputable enough that they're taking it. If you would have heard the story, and I was kind of trying to find the abstract to this study, and I couldn't find it really quickly. I just heard it on the way to work this morning. But it sounded just like a problem out of your homework. I mean, they took a group of this many knuckle crackers and a group of this many non-knuckle crackers, and they tried to see was there a difference. It sounded like the cell phone problem. Here's what how much cancer normally happens. Now let's take a group of cell phone users and see how many occurrences of cancer occurred there. Is it normal? If it wasn't, if I got a lot higher than I would expect, then obviously cell phones might cause cancer. So here they did the exact same thing. Does knuckle cracking cause arthritis? Well, they did a study between those two groups and saw no, they're not outside the range what I would expect. Okay. Yes, ma'am. Sorry.
For the quiz for chapter 6, so that's the only 2 things that you should know.
No, you should definitely be able to do this kind of problem I give you. But remember, there was, if I give you like 3% below, what's the score that would have 3% below it? So you have to be able to do it backwards, that kind of thing. Yeah. So before I get too far, actually, are there any questions from homework? Especially considering we have that quiz coming on Wednesday, 6.2 through 6.5. And then what's happening next Wednesday? Test, yeah. So this Wednesday I'll have the practice test. Next Monday will be review day. Any questions from homework stuff?
Wait, is there a quiz on Wednesday?
Yes, quiz on Wednesday, 6.2 through 6.5.
Oh, and then we're getting the practice on Wednesday.
And then I'll pass out a practice test, yeah. Cool, yeah.
Number 18 on page 46.
Okay. Oh, yeah. Did a certain part of that give you trouble, or was the whole thing?
Yeah, the first part.
Part A?
Yeah.
So, number 18 says, currently quarters have weights that are normally distributed, blah, 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 blah. This is in section 6.5. Quarters have weights. The mean is 5.670. And the standard deviation is 0.062. A vending machine is configured to accept only those quarters with weights between 5.55 and 5.79. Some of you know, back in the day, you ever seen those slugs, those little pieces of metal that are approximately the size of a quarter? And they used to actually work in some soda machines until they realized what was going on and improved their security in the soda machines. And then I would love the scene from Real Genius where he's got like liquid, not liquid, but it was frozen, some ice, some dry ice. And you shave off a piece of the size of a quarter, put it in, and it worked somehow. And of course, the evidence would disappear. Dry ice just goes right to gas when it melts. Anyway, so have you ever seen the movie Real Genius? If you have not, look it up. Watch the damn thing. Hello. All right. And then you can thank me later. So this thing only accepts quarters that are between those two. Here's the reality of quarters. This is their average weight. This is how much they change by. They're varied by. But so this is a big question. How many quarters would be rejected? How many good quarters would be rejected? Because there could be a good quarter that was less than that or greater than that. It's possible. So we just want to see how many would be. How many angry people would we have and wouldn't buy our soda anymore? Right, so part A says if 280 quarters were put into this machine, how many would you expect to be rejected? So the problem with this is, we know what expected value is. What does it represent? Expected value. The mean. Now in this case, I definitely don't have any x's and p of x's and stuff, but I do have a better thing. I can do the mean is NP. Because I have a number. I have 280 quarters I'm going to put in that bad boy. Now if I can just figure out the probability that any quarter would be rejected, I could then do this. Expected value is the mean. So if you can find out the mean for whatever situation you're in, that's what you expect to get, right? So that's what they mean when they say, how many would you expect to be rejected? Well, I have to know what percentage of them are rejected. So this is, I love part A. This part A is like a multi-step problem in itself. You have to first figure out what percentage of them are outside this range. What percentage is that? And then multiply it by n, by 280. What's the probability something will be rejected? Well, rephrase that in stats. To be rejected, what's got to happen? The weight's got to be what? To be rejected, what's got to happen? For this machine to go, no way. Yeah, the weight's got to be less than 5.5, 5.55, or greater than 5.79. So if I do that probability, or means add, so I love this problem because I try to be kind of nice and I try to step out all the steps you're going to need to be able to answer like part D. And the book does that most of the time too. Here's one where they finally said, screw all that shit. Let me just ask you a straight up question. Are you able to figure out the parts you need to do it? Right? This is really more true to life. So in order to figure this out, I have to figure out what P is. Well, what's P? It's going to be probability something's rejected. And now I can figure out how to even say the question then based on how many are going to be accepted. Right? So that's what's going to make it rejected. So how do I do each of those? You find a z-score, you look it up, get the percentage. Right? So here this is going to be, the average is 5.67. I want less than 5.55, greater than 5.79. I want to get those areas and add them together. That's the probability that a quarter will be rejected. Then you multiply it by n to see how many you would expect to be rejected. So it's really the same question if 280 people come up to your soda machine and we're assuming that it's cost 25 cents for a soda, right? So it's probably this big of a can. How many of them will walk away angry? They've got good quarters. How many of them might walk away angry? Yes, ma'am.
What happens if it were like 50 cents instead of 2 quarters? How would you make it work if it was 2 quarters?
Oh, well, the way they asked this is really from their quarters perspective, so it doesn't matter. But if I want to know how many people this represented, then that would just be 140 people, right? And actually, it would be even worse, because then just at least one of the quarters would have to be rejected. So you have to bring in the 1 minus. So thank God we didn't do that. Yeah.
I'm confused about whether we're talking about the area shaded inside or outside, because I thought it's supposed to be...
So this is when the machine will accept it. And this question is all about rejecting it. So this is when it will accept it. When will it reject it? When it's outside of that range. When it's too light or too heavy. Cool. Does that make sense? Because some kid trying to shave off some stuff off a piece of metal probably won't get it quite right. So that's what they're kind of thinking here, I guess. Of course, nowadays they have scanners that can scan and see what the hell kind of coinage you just put in there. How are we doing? Is that decent? I mean, I agree with you. Part A on that problem is really the hardest part, because it's got a lot hidden in it. Okay. So if you haven't gotten there yet to this problem, there's a little head start. Okay. Any other questions from homework? Okay. So now to get into 6.6, and really to talk about this piece of this handout. So I don't know if you remember this handout. Hopefully it looks familiar. We'll come up with more technical ways of showing it's normal. We're going to do that today, finally. And it's going to lead us into parts of chapter 7. So when we did this handout, it was pretty obvious that this looked pretty normal. In fact, back in chapter 3, we would have said, yeah, this looks pretty normal. Right? Don't even have to define it loosely. That looks pretty damn normal. What is it really about this that makes it possible for this to be normal? If I could take one of these coins, remember this is about flipping a coin and getting heads or tails? If I could take one of them and change so it lands on heads more often than tails, so I could change the probabilities. Or if I did it more or less times. I mean, what is it really about this that lets this be normal possibly? For example, if I did this 14 times, like we did on here, but the probability of getting a head was only 0.1, 10% chance. So somebody's weighted this coin, so it's going to land on tails most often. Right? And then you sneak that in for your favorite football team and tell them which one to call at the Super Bowl. Not that that's ever happened. What's the big thing that would change here on this picture? There's a couple things, obviously. Why is the highest point where it is? Remember the situation was, I'm flipping a coin, looking for heads. I'm doing it 14 times. So how many heads would you expect to show up? 7. Why 7? Sorry, I was looking at the wrong person. I don't know.
It's the expected value because it's the mean.
Yes, the mean. N times P is a 50% chance, so 14 times 50% is 7. Not a big deal, right? Well, what if P is in 0.1? Now what's the mean? 1.4. So then where would the highest bar be? What whole number is that closest to? 1. So the highest bar would now be at 1. So I'd have 0 with something. I have 1 with the highest bar. So 0 would actually be higher. And then 2 would be lower. 3 would be even lower. Does that have really any chance to be truly normal?
No.
So what really made this normal is that the probability was close to 50% for one thing. But more importantly, N times P was big enough to pull it away from this wall. If NP was really small, then it could look like this. There's no damn way that's going to be normal. So you have to give it room to go up and then come back down. Does that make sense? So here NP was 7. That gave it room to grow and then shrink. It could have probably been a little bit less. And it had room to grow and then shrink. You also don't want this thing running into the other wall. And why are there walls anyway here? What's the lowest number of heads I could get?
0.
What's the highest number of heads I can get?
14.
14. So either I could have something where the mean is just so small that happens. That's never going to be freaking normal. Or I get the mean so big that happens. That's never going to be freaking normal. So I want to pull it in towards the middle so it's got room to grow and come back down. So what that really means is I need my mean to be greater than something. And alternately, I want the how many successes I have to be bigger than something, but how many failures I have to also be bigger than something. So it comes right in the middle. So what happens here is for a binomial distribution, oh boy, it seems like it to be approximately normal. NP and NQ have to both be bigger than 5. We've never really looked at NQ, but if NP is the number of heads I expect, NQ must be the number of tails I expect, or even more generally, the number of not heads I expect. Right? The number of failures I expect. You guys kind of with me? Does it make sense at all that if both of those are true, it's going to pull it away from that wall, and it's also going to make sure it doesn't run into that wall. So then it's got room to grow and shrink. That's the whole idea. It's beautiful. It's very visual. Thank God. So if you have a binomial distribution, and I say, is this normal enough? That's what you check. So why the hell would I ever want that? Why the hell would I ever want to see if a binomial distribution is approximately normal? I don't even want to say that. It takes forever to say it. Well, here's one situation. 89% of stats students think they have too much homework, when in reality it's not enough. So 89% of stats students think they have too much homework. We randomly select 4,000 stat students. What's the probability that more than, what, Jeff? I don't know. 3,217 will think they have too much homework. Now, can somebody please tell me, if we tried to do this problem the way we've been doing these kind of problems, how much work is involved here? Can you see how much work is involved here? What answers this question? What situation would actually match this? I find 3,218, or 3,219, or 3,220, all the way up to freaking 4,000. How many times do you have to do this formula then? You have to do it for 3218, 3219, 3220, all the way to 4,000. So over 700 times. Holy crap. No, thank you, Jeff. You guys with me? Okay, cool. So I'd much rather realize what we just talked about. The fact that I can get a mean. What's the mean in this case? What's N? What's P? P is 0.89, I love it. So what's N? 4,000, 11. And what's Q? 0.11, 11. It's cool. So you can always get those from the problem. The problem is kind of telling you I'm a binomial problem. Here's an N, here's a P. Get N, P, and Q and go to town. I don't want to do it the way we've been doing it, because it's way too much work to do. Holy crap. So I'd much rather say, okay, if I can get a mean, what's the mean going to be here? How do I set that up? Good. N times P, which is like 3,560.
Yeah.
I'm a math teacher, come on. Got to show off every now and then. That's all my skill right there. And what's the standard deviation going to be? Can you do that one, Jeff? I don't know. I think it's about 17. Not too far off, right? 18.87.
I got 19.7.
19?
19.789.
19.789? Okay. No worries.
We have the formula written in excuse me.
Oh, that guy there?
What's the, between the N and X above the Q? Is that?
It's right there, Q.
There.
Right? Cool. So that was the formula we were using before, right? And we're still going to use it a lot because it's still useful. But in this case, good God. So I'd much rather say, all right, I know this is binomial, but if it was normal, couldn't I use z-scores and look at the formula in the chart and be done with it? Normal distributions have a much better, have something over these. I don't have to find this one and this one and this one and this one and add them up. I just look up a z-score and I'm done. That's the beauty of normal distributions. You with me? So if I could just say, okay, I know it's binomial, but just let me say it's normal, because then I can find, I have a mean, I have a standard deviation, I have an x. Can't I find a z-score then? And go to town on it? Does that make sense? This specific one, I picked a bad number here, but I was trying to make a point. I don't know if you guys realize, how far away is that from the mean, relatively? Pretty damn far away. Can you guys see ahead that my z-score is going to be huge? Can you see what I mean?
Yeah.
All right, so this is not the best example in the world, but the process is still good. So I should be able to get, okay, I know this is binomial. It looks like this, blah, 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 blah. It's got a lot more freaking rectangles, so there's a lot going on. But right in the middle, what is this bar going to represent? 3560. You with me? So let's check first. Let's do our check. Is it normal enough to do normal stuff with it? NP, we know what that is already. That's 3560. And it's got to be what to be normal? Greater than 5. So it definitely is greater than 5. Check mark. What's NQ? So 4,000 times 0.11 is 440. Why does that make sense? This plus this is 4,000, right? If the number of successes have to add to the number of failures to make the total. That's kind of cool. But that's definitely greater than 5. So this is normal enough to do normal probability stuff with. The one thing we got to be careful about, and this is where I want to slow down and focus on this, is, for example, if I said at most 6, like we did last time, when we did this, we got that probability, right, just from adding up stuff. If I want to go up to 6, why can't I not say this is normal? What's one big reason I can't say this is normal? I had to draw these stupid little histograms, right? And the normal curve, of course, has a very smooth thing going on. Why is that true? What kind of data is this versus what a normal distribution shows? What kind of data is this? Oh crap, this is a chapter 1 problem. What kind of data is this? Can you have 8.394 heads? Hell no, right? So what kind of data? Discrete. And we want it to be continuous. This is discrete freaking data. I can't draw it using that. That's continuous data. Shit, so I need some kind of a correction for that. That's the only thing I'm missing. I've got a mean, I've got a standard deviation, I know it's normal enough, but the problem is it's not actually really normal. I have to kind of correct for that. I have to correct for it not being continuous. Okay. So here's what we do, and this is kind of funky. This is called the continuity correction. All right, that name makes sense, thank God. We're correcting it because it's not continuous, and we need it to be. And basically, I've already kind of made it continuous. The problem with discrete data is there's gaps from 6 to 7. But what have I done here? I said that 6 is not really 6. 6 is from 5.5 to 6.5. And then 7 is from 6.5 to 7. So they do run together. So it does look continuous. And it's that stupid simple. So if I want to do that problem again, probably at most 6 heads. Which more mathishly, this would be less than or equal to 6, right? At most 6 heads. Yes, and mathishly is now a word. Then I want to actually, I've got to be careful. I know the mean is 7. I'm interested in 6, but I've actually got a bar there. That whole bar represents 6. Do I want to include 6? In my question, do I want to include 6? So the whole question really is, do I shade up to 5.5, or do I shade up to 6.5? Which one would include 6? 6.5. There you go. So the continuity correction is this one silly step. Change the question into that. That will account for that missing. If I just did from 6, wouldn't I be missing this much area? It wouldn't really be good then. So this continuity correction makes this a much better approximation. It includes that extra area that I would be missing. So let's do this. Let's do it both ways and see which one's right. We know the answer is 0.395. That's the answer. There's no getting around it. So I want to see which one of these comes out better. And this whole process we're doing is called, you're going to love it, the normal approximation to the binomial distribution. The normal approximation to the binomial. It sounds like I'm a Jesse Jackson giving a speech. I love it. So what I normally call this thing, just to get to the point, is I call it a NAB. It's a NAB problem. NAB. Normal approximation to binomial. It just takes too long to say all that. And that really is what we're doing. We're trying to approximate a normal, a binomial with a normal. We're trying to have a normal approximation to this binomial, because I don't want to do all this work that's involved very often. I want to do much less work. I want to use the z-score to get the answer. So if we do that, let's do this. First, we'll do it the right way. So the continuity correction on this says to make this become 6.5, so that it include the whole 6th bar. Does that make sense? I have to include that whole 6th bar. So if I go up to 6.5, I'm going to include the whole 6th bar. Okay. So now the great thing is, all the steps are the same now. I make a z-score. What do I make a z-score out of? 6.5, not 6. Right? So remember, the mean here was 7. The mean for this problem was 7. Standard deviation was, I think we calculated it, 1.871. Remember, we did the square root of NPQ. So we make a z-score out of 6.5. Somebody help me out there.
Negative 0.27?
Sounds about right. So you guys are getting negative 0.27 about? About. All right, so look up that z-score now and get the area. If I look up negative 0.27, I get an area of 0.3936. So make sure you can find that. If you look at negative 0.27, do you get the 0.3936? And just make sure we're all on the same page, literally and figuratively. Well, you got to be on the same page for that, John. Negative 0.2, and then 7 is right there. There's 7. So it's 0.3936. Is that cool? You can see that? All right. Let me keep that there for a second here. So what was the answer really? What was the real answer? 0.395. We did that using binomial techniques. we got the n choose x for each one of these. We got it from the table. Who cares? We could have done that. That's what they did. And added them all up. That was a lot quicker, really. Well, a little bit quicker. So we got 0.396. It's supposed to be 0.395. That approximation is pretty damn good. Now, if I would have made a mistake and forgotten to do this, would that really throw it off that much, Jeff? It's only off by a half then, dude. What the hell? Ease up. It does sort of depend, but not really. It will always be worse. It just depends on how much worse. So if I would have forgotten to do this, everybody with me? If I would have forgotten to apply that continuity correction, if I would have used 6 instead of 6.5, my z-score would have been whatever that is, so twice this really, so negative 0.54. You just take my word for it, you can check me, you never know. Right, because this is a half on top, this is a 1 on top, so it's going to be twice as much as that one was. So negative 0.54. So now I'm actually twice as far away, really. So when you look up negative 0.54, I get an area of
It'll be negative 0.53.
5.3? Oh, because the rounding for there? Thank you. So 5.3. So if I look up negative 5.3, what do I get here? 0.2981, yeah. So if I forget to do the continuity correction, I get a probability answer of 0.2981. Is that close to what it's supposed to be? It's almost 10% off. Holy shit. To make it a good approximation, I need to do the continuity correction. So I know right now you guys are like, okay, what the hell just happened? I desperately want you to realize that last section we did, in the work, what's the only thing that really changes? You change the standard deviation. Everything else is the same. You make a z-score, you look it up. On this kind of problem, a NAB problem, and yes, I will be as nice as on a test to say, use the NAB to blah, blah, blah. That's pretty damn nice. So appreciate it. So when I have a NAB problem, the only thing I do is change the question, depending on if I want to shade the block in or not. And then I make a z-score out of it, and I look it up. All the rest is the same. It's one little tweak to the problem. It's almost too easy to trust. It can't be that easy. So real quick, I want to focus on the part that gives people the most trouble, really, which is that continuity correction itself. So let me do a couple with you, and then I'll give you a few to try on your own. So my question was, x greater than 11. How would I apply that continuity correction? Well, what you do is, you draw a little picture. Here's your 11. Here's your box. Do I want to include the 11 box? This is going back to algebra. Since it's strictly greater than, do you want to include 11? No. Hell no. So when I shade, which way am I going to shade? Up, because that's the way it's pointing, right? So I'm going to shade up. Do I want to start at this back wall or this front wall? Front wall, because if I start back here, I'm going to include the bar. I just said I don't want the freaking 11, so I'm going to shade there. So when am I going to change this number to? 11.5. If you take 5 seconds, draw the picture, think about it, bam. Don't memorize anything that's insane. When it's less than or equal to, it's going to go there. When it's greater than or equal to, no, that's crazy. Just draw a little picture and think about it for a second. So this would have to become, through the continuity correction, this would be greater than 11.5. And make a z-score out of that and go to 10. So you guys try these. All I want is to know, what would the continuity correction itself do? Just by itself. Let's see, 5 seconds each. 2 problems should take you 10 seconds. What you're comfortable with. It's really not that big of a deal. If I want less than or equal to 99, do I want to include the 99? Yes, I do. I'm going to shade up or down? Down. So it's a question of, do I want to start there or do I want to start here? Do I want to start there or here? Here. I like it. The back wall. Because I want to include the 99, right? You guys get the feel for this? I want to shade down, so I can only start here or there. I want to include the 99, so of course I start there, which is 99.5. So the continuity correction would make this 99.5. That's what I use to make a z-score and then look up that z-score, so forth. That's why it's so important for you to understand the basic z-score problem. Make a z-score, look it up, make sure it's the right area. Because what do we start to do? 6.4, 6.5, we messed with it. All right, guess what? Now you got to make sure you got the right standard deviation. 6.6, we messed with it again a different way. Okay, guess what? You got to make sure that you change this number the right way. So if you don't understand the basic process itself, how are you going to be able to handle freaking change in certain parts of it? All right, so you have to understand 6.2, 6.3. Okay, what about this last guy? Do I want to include the 13? No. And I want to shade, down. So I don't want to include this. I don't want to start there. I want to start there. So I do not include the 13. So this becomes 12 and a half. Cool. I love it. Now, some of you guys, real quick, just to kind of freak a few of you out a little bit, but hopefully this answers a question that might be in some of you guys' heads. Why before did it not matter here? Well, let's make z-score a little bit. If I say z less than 1, it really doesn't matter if I say that. It doesn't change at all. It doesn't change a damn bit. Because if I say 1, how much area does this line have? How much area does something that's one-dimensional have? 0. I love it. Length times width. Well, the width is 0. So does it matter if I include the 1 or not? Doesn't matter a damn bit. But the minute I have something that's not continuous, oh shit. Each bar has a width to it. Now it totally matters if I include it or not. Are you guys with me? I don't know if anybody was thinking about that. And you're like, I understood it all till you said that, Jeff. Shit. Don't worry about that. It's not a big deal. But just so you know, that's why we didn't care about the less than or equal to or whatever sign before. Because it didn't matter. It's an area of 0. Who cares? Put it in, put it not. Who cares? Okay. So let's try a full-out problem. And this is section 6.6 again. This is what these are going to look like. Well, let me ask this. How many of you guys crack your knuckles? Anybody crack your knuckles? All right, me too. 1, 2, 3, 4. All right, like about 15. So what's 15 divided by 40 real quick?
37.5.
Yeah. So let's say 37.5% of all stat students crack their knuckles. It's a very meticulous study I just did. Alright, but we're all cool with that. Let's just say this is actually the truth with that. We randomly select. Makes it sound like a pick. We randomly select 723 stat students. And this is how I put it on a test. Let me show you how I put it on the test. Check NP and NQ. It's not a QJAP. For normality. Okay? And then I'd say, use the nav to find the probability X is what, I don't know, greater than or equal to 257. see if I picked a good number. I don't know. And actually, to be completely honest, I would even ask you to separately find the mean and the standard deviation. That would be even nicer than all that. It's just crazy how freaking nice it is. So what does this mean? This first question. What do I have to do here? Yeah, you just look to see if they're bigger than 5. And in the process, I get NP, which is the mean. That's beautiful. All right, 2 for 1. So NP is what here? What's N? 723. What's P? 0.375. So what's Q? 625. That's right. So what's NP going to be? 723 times 0.375.
271.125.
I got pretty close. Okay. 271.125. Is that all good? Everybody else says, I don't know. It's good. All right, and so that's definitely greater than 5. So NQ will be 723 times 0.625, or just 723 minus this. It's got to be the rest. 451.875. And that's definitely bigger than 5. So what the hell does that tell me? It's normal enough. Normal enough to use a z-score chart if I want to. Okay, so that's checking it for an amount. That means it's in the middle, it's got room to go. The rectangles get bigger and then smaller. Sweet. So if I were to graph this thing out, so to do this part, I've got the mean. Well, you can't do that. You can't write that. You barely write this one. I've got the mean is, where'd it go? 271.125. What's the standard deviation going to be? Just do NPQ and then take the square root.
$13.017.
13.017. Is that like good? Now here are a few buttons. Somebody's just hitting buttons to humor me.
Yeah, it's 13. Yeah, that's what it is.
Sweet. All right. So now I can graph this bad boy. I've got the mean, so I know what goes right in the middle. I said it's normal enough, so I can go ahead and draw a normal curve. Here's my mean. My data point I'm curious about is greater than or equal to 257. So I draw a little rectangle in that. Do I want to include that rectangle? Looking at the question. Do I want to include it? Yes, I do. Greater than or equal to. And I want to shade up. Good. To the right. So I don't want to start here because that would not include it. So I better start here and shade. So what number do I actually have to use?
257.5.
Careful. Below. So 256.5. That's the continuity correction. That's just making the approximation actually good. So as you're trying to use a continuous thing for something that's not continuous, you better adjust for that. That's all the continuity correction is. It corrects for that. So now I want to make my question really, what's probably x is bigger than or equal to 256.5. Now I make a z-score, I look it up, I subtract it from 1. Same stuff. That's the one little thing that changes. So z-score is going to be my data point minus the mean divided by the standard deviation it's like 1.0 something.
Negative 1.12. Negative 1.12.
1.12. Then you look that up, you get the area, you subtract it from 1 because you want the area on the other side. right? Once you hit this side, is the, I call it the, for my algebra student, I call it SDT sometimes. It's the same damn thing. It doesn't matter where it came from. Get the z-score, you look it up, you make sure you get the right area. So when you look at negative 1.12, you get 1.12, I get, yeah, good, 13, 14. So that's here. So what's this going to be? Oops. 1 minus that. 8686. Sweet. All right, now very quickly, how do I check that? This is a binomial problem, right? My calculator has binomial functions built into it. So I should be able to use one of those to help me check this work. I don't want to turn him off. Let me see if you guys can see this. All right. This is the old new school. That's not too bad, actually. So if you go into second distributions, you can go to binomial. Now, which binomial do I want? PDF or CDF? C, I want a range of stuff. And in fact, CDF always goes from 0 to something. So I can double check this number here and then do 1 minus to double check that number there. I want to go from 0 up to, now here's the interesting part. What's the opposite of this question, really? The opposite of at least 257 is at most 256. What does 257 or more leave out? Starting at 256 and down, right? So in the calculator, I can do binomial CDF, N, what was that? 723, P, 0.375, and I want to go up to 256 to check this side of it. Calculator can only do 0 up to something for CDF. So I want to do CDF, N, comma, P, comma, up to 256. And let's hope to God it should be close to about 13, 14. Kick ass. That's pretty damn close. I'm off by 0.1%. Right? So then 1 minus that, of course, will be close to the 0.8686. That's pretty damn close. That's the exact right answer. That's the approximation. You guys with me? So don't think that that check will tell you exactly. It should just be close to this. Okay, this is always going to be just an approximation because I'm trying to use something that I really shouldn't be able to. Well, we checked it all out. We said, yeah, we can use that. We can get pretty close. The huge thing to get out of this, probably the most important thing, you have to be able to do this whole problem. But the thing that's going to come back more and more later is this. Because again, what's probably the most important thing now that we've gotten through chapter 6 in statistics is it normal enough to do stuff with? That's the check I take to see if it is normal enough to do stuff with. Okay.
Why did you do 256?
Because binomial CDF only understands from 0 to something. So where would this go? What would this side go? From 0, not up to 257, because 257 is on this side of things, right? The question really is greater than or equal to 257. So what's the opposite of that? From 0 up to 256. That's what it leaves out. Okay, so if it would have been greater than 257, then I would have done binomial CDF up to 257, because it would have left out 257. How important is it to be able to do this? Not. This is just if you want to be able to check yourself. If you don't care about that, cool. You don't have to do that at all. Okay. So I do want to do, seems like enough, but no, not for me. I do want to do a little preview of chapter 7. And remember that none of this is going to be on the quiz. All right? Never do anything on the quiz that we just talked about. Let me ask you around 2 questions. I want to leave things open for myself before we leave, just to get us ready for chapter 7. If you look at your z-score charts, and I think you've had questions like this in your homework, or they danced around this. Can anybody tell me what these z-scores are that bound the middle 90%? Let me say that again. Those 2 z-scores that bound the middle 90% of data in a normal distribution. You with me? So whatever that is, if that's negative 1.8, that's going to have to be positive 1.8 because of symmetry. You with me? So they want to bound the middle 90%. How in the hell do I find that? We could totally do this. This is a section 6.2 problem, actually. Totally do this. How do I get either one of these z-scores? What's the only thing the chart understands? Below. I love it. And what do I have? I have an area sitting in between. So how do I make it into an area that my chart would understand? For example, what's the area below this? 5%. I love it. There's 90% in there. There's 10% outside. There's 5% there. So now I've got it into a question of that the chart will understand. If I look up 0.05, and where do I look it up? I don't look at 0.05. That's crazy because that's not a z-score. That's an area. So what's the closest you can get to 0.05? Looks to be a little asterisk, dude, right? Oh, not 0.005, Jeff. You can do it. 0.05. Here it is. So right in between 0.0505 and 0.0495, that's 0.05. Are you with me? So again, if I want the middle 90%, my chart is useless with any area that is not something below a z-score I want. Well, that's one of the z-scores I want. If I know him, I know him. So what's the area below this dude? Well, 5%. It's got to be 5% below this dude. So I can find him easy enough. So we get right in between 1.64 and 1.65, so that's why it's 1.645. So if he's negative 1.645, who's he? Positive 1.645. Ooh, it's amazing. Right? So you say the 2 z-scores, negative 1.645 and positive 1.645, have 90% of the information between them. So how confident are we that any individual data point actually is in here? How confident are you? It's a weird question to ask. How certain are you? That's a synonym for confident. Yay. How likely is it that a data point falls in here? 90% chance. So we were 90% confident that any specific data value is in there. Why? Because there's freaking 90% of the data in there. I'm using the language you're going to use in Chapter 7. Chapter 7 is all about making confidence intervals. Because what happens normally in statistics? Normally in statistics we get a x bar, but we really, really want a mu, right? I talk to a bunch of people so I can find out and get a feel for what the real average is. Well, now we're finally to the point where we can say, all right, if I get a mean of 12, I want to make it to the way I can say I am 90% confident that the real mean, that mu, the real population mean, is between 11 and 13, maybe. That's a possible outcome of Chapter 7. That's pretty powerful. I'm 90% sure that it's between 11 and 13. So what's the chances I'm wrong? 10% chance that it's not between 11 and 13. You with me? We're finally getting really close to where they get the freaking plus or minus 4% at the bottom whenever you see a poll. 44% of people want to increase gun control laws, and 38% of people think that, there's too many gun control laws, whatever. At the bottom it says plus or minus 3, plus or minus 4. This is exactly where we get the plus or minus from. How far out do you go to be this certain? This is what they never tell you. They never say 95% confidence or any of that. They don't tell you how confident they are behind the scenes. They just give us these numbers, the 11 to 13. Right? And then people look at the poll and say, there's no way this guy's going to win. He's got 47, he's got 40. No, they don't know. Plus or minus at the bottom, that's not even right either. It's at a certain confidence. There's always a chance. Anyway, I've gone too far. That's chapter 7. We're going to really get into the workings behind this. So we'll do some more now. Have a little handout next time. We probably won't make it all the way through chapter 7, because section 7.4 is really thick with new ideas. So that will probably wait for after the next test. Okay.
Can we have you put calculators on that one section? The binomial distribution one?
Oh, cool. Sorry.